When we observe galaxy clusters, we see the galaxies swarming around in a somewhat chaotic manner, but one thing we don't really pay much attention to is the diffuse light between these galaxies, but in my opinion, I think they're just as important as them. Hi everyone, and welcome back to the channel, and welcome if you are new. You might notice I'm in the exact same setting as I was in the previous video, and that's because for the past few days I've decided to take some time off to relax and spend a couple nights in this really amazing caravan over in the middle of nowhere. Today we're going to be looking at something called the intracluster light and its potential to map out dark matter. I think when it comes to orbits and gravity in general, our first example that comes in our minds is usually the planets orbiting around the sun. In this case, it's actually quite simple because the sun is many orders of magnitude more heavier than the planets, yes, and even Jupiter. So when it comes to all of our complex equations regarding gravity and the motion of, massive bodies, it all really simplifies down to just focusing on the sun's properties. However, when we go a step further and look at, say, a star inside a galaxy and its orbit, we don't only consider the mass of the supermassive black hole, because we've also got all those stars within that orbit that also contribute to the general mass and gravity, and thus the orbit of the star that we're looking at. The number density of stars goes down as we move further and further away from the galactic center, and this makes sense with observations. We see that the edge of the galaxy is much more sparsely populated than near the center, so we expect the velocities of these distant stars to be much slower as they orbit round the galactic center, matching the curve that we see with the planets. But we actually don't. We find that these stars are usually moving, at roughly a constant velocity regardless of the distance once you get out to a certain distance, and sometimes even more than that. This suggests that the mass is actually roughly proportional to the distance from the galactic center, and this completely contradicts what we actually see with the amount of stars that we're counting. Hence, this sort of phenomenon actually gave rise to the idea of dark matter halos surrounding galaxies. Clusters can be even more of a complex beast, because while galaxies can have their own halo, they can also share common halos with neighbouring galaxies as well. And what we find is that a cluster can also be shelled within halos, and halos can also connect with little filaments to each other. So how do you really explain all of that? Clusters are completely infested with dark matter. We've seen this through gravitational lensing surveys time and time again. What we can also say is that galaxies tend to make up roughly around 5% of the mass. I've seen 1% being thrown around here and there, so add a little bit of percentage error as well. And then we also see that the dark matter makes up roughly around 80 to 90% based on gravitational lensing. But you've probably already noticed that that doesn't actually add up to 100%, there's something else going on. We also have the intracluster medium, or ICM, not to be confused with the interstellar medium, or ISM. This makes up the majority of the baryonic matter, so that's the non-dark matter, and it also lives between the galaxies, not inside them, hence they're called intracluster. It's mostly made up of very hot ionized hydrogen and helium plasma. We can't see it all that well in the optical, but we can see it very, very well in the X-ray. The ICM also has quite a lot of ejected or rogue stars which have been swung out of their host galaxy and just added to this pool between the galaxies. And these little stars also light up the medium fairly dimly, and this light is called the intracluster light, or ICL. So what has this actually got to do with dark matter? Well, these stars, which are now no longer bound to a certain galaxy, are just generally bound to the general gravity of the cluster itself. So we can treat them as lone particles that basically just move according to the gravity of the cluster. But guess what also does this and also makes up the majority of the mass in the cluster? The dark matter halos. So this ICL, these stars, should be moving accordingly with the dark matter, because they both obey gravity, and so they should essentially stick together fairly well. Not quite literally, but they should be moving together accordingly, and so we expect that ideally these stars should actually trace out where the halos are, at least. It's kind of weird, but it does sort of remind me of bats and dolphins, because they use echolocation, or at least bats do. And, they don't have very great eyesight, and so they can't really see in the dark. So they can't see things like, for example, a tree. We can think of the tree as dark matter in this case, but they use echolocation, they use sounds to sort of, sound out and see where the sound bounces back at them, and the time delay between that tells them how far away it is and some other properties. So we can think of these intracluster-like stars as sort of like sound, sort of mapping out where the dark matter or the tree is in this case. One of the first papers I read was way back in 2017, and at the time it was a recent paper published by Montes and I believe it's Trujillo, or maybe Trujillo, I'm not sure which one of it is, I'm really sorry. And they looked at, of course, how well the ICL may be able to trace out dark matter as, just a general tracer. And then the following year they released an absolute goldmine of a paper. They looked at how well the intracluster light traces out the dark matter halos and just the general mass distribution of clusters as determined through the X-ray gas and gravitational lensing. They found that the ICL indeed was actually a pretty good tracer of the dark matter halos based on just the cluster that they were looking at. You can actually see that these outlines match each other fairly closely, but you also need to bear in mind that a lot of the techniques, so the ICL tracing, the gravitational lensing, and the X-ray tracing all have their own errors as well. Each of them have their own errors, which all need accounting for. Montes and Trujillo have done a significant amount of work within this specific field of astrophysics. I couldn't go into all of their work today, we'd be here forever. But more recently there was a paper by Diego et al., I believe, and they looked at the cluster SMAC 50723. And this was done using JWST as well. And they found that at large distances from, the center of the cluster, the ICL doesn't really match the visible mass very well. Hence, their finding sort of points towards, I guess, a need for a dark matter halo explanation. Overall, I'd say it's looking pretty positive for the idea of the intracluster light being a tool to map out dark matter, or at least trace it out. The papers that I've recommended and I've just talked about are of course going to be linked below in the description, but I really recommend doing some of your own reading as well. And I also recommend specifically the intracluster light and its role in galaxy evolution and clusters, which I think is the full title, by Montes once again. And that's because it's a really fantastic resource. It goes into specifically the origin of the intracluster light and the medium as well, of course, its evolution and of course its history as well. And it's also got a very long list of references. So if you want to go and do even further reading, I do recommend looking at that one. It's so remarkable to see how fast a certain field in astrophysics can grow within the span of, just 15 years in this case. And we've also got the Euclid mission and the LSST, which I believe is going to be adding a lot more data and information to this pool that we can also use as well. So definitely keep your eyes peeled for that as well. Thank you very much for joining me as I talk about the intracluster light and dark matter. If you like the video, please like it, and if you like what I talk about, I highly recommend you subscribe. It means a lot to me, and I would absolutely love some more company as I talk more astrophysics and just general spacey stuff. And with that, I will see you very soon.